welcome back. This is lecture 12. So in the previous lecture, we were trying to build an amplifier which was supposed to give us some amplification of power using a MOSFET, and we noticed that in order to arrive from the small signal incremental model of our MOSFET to a full-blown MOSFET architecture with all the biases in place, we had to make some adjustments in order to accommodate for the required quiescent conditions, right? And we were halfway through, because what we said was under the given conditions that we want a gain of, let's say, 10 across a resistance RL of 1 kilo ohm, we saw that we required a GM or a Y21 or a GM of the transistor to be 10 millisiemens. From there we back calculated the required overdrive, that is the VGS-Q minus threshold voltage. From there we got the value of VGS in order to get a GM of 10 millisiemens, right? And that VGS came out to be 6 volts. Then we had to ensure that that 6 volt VGS remains applied, right? I mean the incremental signal that the incremental signal that we are trying to amplify should be riding on top of the VGS, right? We cannot just simply apply the incremental signal to the gate of the transistor, because the transistor will not be on. Okay, and then we came up with the architecture of the input loop, right? And then we saw that if we do this, not only we will have a quiescent current of 25 milliamps. So this is quiescent, this is IDSQ, but also we will have incremental current IDS, and the total current will be the quiescent plus the small signal incremental. And note that if we go back to lecture 11, you would have seen that the way we came up with this incremental topology or the mathematics behind this was we used the full-blown equation of the MOSFET, assuming that MOSFET is in saturation, and then in the full-blown equation we neglected the higher order terms, right? So that in essence is the approximation, a small signal approximations. We haven't yet seen under what condition of VI that small signal approximation holds, but we have assumed that, let's assume that the VI is small enough for the small signal approximation to hold. So we will go back later and see under what condition in a MOSFET the small signal approximation holds good, right? For the time being, we will assume that the small signal approximation holds, and we will simply say that the total current, right, the total current flowing between the drain and the source is the quiescent current plus the small signal current, the incremental small signal current, that is GM times VI. Okay, great. Then we turned our attention to the output side. What is the output? The output is across RL. Now what do we see at the output? What is the voltage across RL? Clearly the voltage across RL is 6 volt, because I have a battery clamped across RL. So regardless of whatever incremental or changing current that flows through the MOSFET, it will not be able to change the voltage across RL, right? So what is the solution? So putting RL in parallel with the battery doesn't seem to be a solution. I mean, if not in parallel, what is the other thing that we can do? We can try putting RL in series with the battery. So let's do that. So if we put RL in series with the battery, let me get rid of these details. So let's put RL in series with the battery. Same battery, 6 volt in series with RL, right? So what do you think will change? Or I mean, the first thing we need to see, moment you change anything in the circuit, the moment you change anything in the circuit which can potentially change the quiescent conditions, you need to go back and check whether the quiescent conditions under which the transistor is supposed to work still holds true, right? For example, in this case, what do we want? We want the transistor to remain in saturation, right? Regardless of whatever happens. Okay, unless the transistor is in saturation, we are not going to get any amplification. So it is imperative to always ensure that the transistor remains in saturation if we are looking to get gain out of the amplifier. So since we have moved the battery, we now need to check whether the transistor remains in saturation under quiescent condition, right? So basically, first thing is check operating point, right? So how do I check operating point? There are 3 operating regions. One is cut off, right? One is off, transistor is off. One is it's in linear region, which is also, by the way, called triode region, and another is saturation. So what we will do is we will not try to assume, we will not try to derive whether the transistor is in saturation or triode or whatever. We'll assume a region of operation and then try to see whether the assumption holds true or not. Okay, so this will be the recurrent theme through the course. So we will assume that the transistor, I mean whatever we are trying to achieve is going to work, and then we will backtest our idea and see whether the assumption holds true or not. Okay, so let's assume that the transistor is in saturation, right? So we will assume MOSFET is in saturation. Okay, so if the MOSFET is in saturation, what is the current what is the quiescent current that is supposed to flow? Note, I am not talking about incremental current, which means I am assuming that Vi is 0, right? So we can as well put Vi to be equal to 0, right? Because we are doing quiescent analysis. So when we are doing quiescent analysis, this is regardless of whether you have applied a signal or not, right? So in case of a voltage source, we need to desensitize the voltage source, and desensitizing the voltage source means we have to short circuit the voltage source. Okay, great. So now if we assume MOSFET is in saturation, what will be IDSQ? So you can look back in your notes of the previous lecture. Your IDSQ, assuming saturation condition, will be half nu n Cox W over L. VGSQ, that is 6 volt, minus threshold voltage, that is 1 volt whole square. And if we do this calculation, what did we get? We got 25 milliamps. So this is supposed to be 25 milliamps, assuming saturation condition. Now we need to go back and check whether the saturation condition is indeed true or not, right? So what do we need to check? What is the test for saturation? The test for saturation is we need to check the drain voltage, we need to check the gate voltage, and we need to see whether the drain has gone down 1 threshold voltage below gate or not. That's the only thing, right? Note that we need not bother about the source, right? Saturation condition, the saturation condition is VDS should be greater than VGS minus threshold voltage. Source is common on both sides of the non-inequality. Source goes off. So essentially we need to satisfy, check if VD is greater than equal to VG minus threshold voltage. Again, note that you need not bother about the source voltage, right? Source can be anything. In this case, it's trivial. In this case, source is grounded. But you will see later on, we will have topologies where source is not grounded. But you don't, I mean, when you are trying to figure out whether the transistor is actually in saturation or not, you need not bother about the source. What do you need to bother about? You need to bother about the drain voltage and the gate voltage, right? The absolute drain voltage and the absolute gate voltage, and see if the condition of VD greater than equal to VG minus threshold voltage holds or not, right? So let's assume, let's see whether it holds or not. So this is 25 milliamps, right? So what should I do? If we assume IDSQ is 25 milliamps and you have a battery of 6 volts, what is the drain voltage? What is the drain voltage VD now? So you have this voltage is 6 volt minus RL times IDSQ, which is how much? RL is 1 kilo ohm, IDSQ is 25 milliamps. Essentially 6 volt minus 25 milliamp, 6 volt minus 25 volts, that is minus 19 volts. So clearly this is not in saturation. Not only that this is not in saturation, this is telling us that the drain is below ground, right? Which clearly is not possible, right? Because if you have a circuit where the minimum voltage is ground, it cannot go beyond that, right? And I mean, if you have an LTI circuit, right, where you are not purposefully trying to get a voltage lower than the ground or higher than the VDD, you will not get a condition where under DC operating point voltage is minus 19 volt. Okay, so which means that assumption is wrong, right? So in this case, VD is equal to minus 19 volt, which implies saturation assumption is wrong. Is incorrect. Okay. So if it's not in saturation, obviously it must be in linear, and we need not go about and figure out how deeply in linear region it is, because we are not bothered about linear region at all. So all we need to care about is what should we do in order to bring the transistor back into saturation region. Okay, so next thing will be modify biasing point to get MOSFET back in saturation region. Okay, so what should we do? How can we get it back to saturation region? What do you think needs to be done? So clearly in a saturation region, the only thing that is sacrosanct is IDSQ has to be equal to 25 milliamps, right? So if I only concentrate on this part of the circuit, right? If I only concentrate on that part of the circuit, what should I see? I should essentially see that I want an IDSQ of 25 milliamps, correct? This is we want, right? If it's in saturation, this is what it's supposed to be. And since What is a transistor? A transistor is a current source, is a voltage controlled current source, but it's a current source nonetheless, right? So we can essentially replace the transistor with a current source of 25 milliamps if it is in saturation. Then what? This is supposed to go through a resistance of 1 kilo ohm, and we are supposed to have a battery here. Let's call this battery VDD. Now, what all things are negotiable here? What all things you can change and what all things we cannot? Clearly, this cannot be changed. When I mean it cannot be changed, what I essentially mean is that this has been fixed by a specification, right? We came to this IDSQ not just by fluke. It was a requirement of it came from a top level requirement, right? We started off with a gain of 10 across a resistance of RL. We know the gain is GM times RL, which means if RL is 1 kilo ohm, GM has to be 10 millisiemens. From the value of GM of 10 millisiemens, we figured out what the VGS needed to be, assuming certain value of W by L. We figured out what the GM needed to be, or rather we figured out what the VGS needed to be. From that VGS, we back calculated the required IDSQ, which means we need this much IDSQ, right? So we do not want to change IDSQ, because if we change IDSQ, our GM will get affected, which in turn will affect our gain. RL, can we change RL? We cannot change RL because RL has been given by a specification that we need to get a gain of 10 across RL. So RL we cannot change. So what else can we change? Obviously we can change VDD, right? So now the question boils down to, what is the minimum VDD, right? Find VDD minimum for which, let me call this MOSFET M1 instead of repeatedly writing MOSFET. M1 is in saturation, right? Why do I say minimum? Because clearly 6 volt is not sufficient, which means I need higher and higher VDD, right? So the hope is that if I raise the VDD, the transistor will go closer and closer to saturation, and then we will reach that magic VDD value for which the transistor is actually in saturation, right? So what am I looking for? I am looking for the transistor to be in saturation. Then what is the required voltage at the drain for the transistor to be in saturation? So required, what am I asking is, what is, this is VD, what is the required VD? So clearly the required VD, that is the drain voltage, is required VD has to be greater than or equal to the gate voltage, which is 6 volt, minus, let me write it in this form, VG minus threshold voltage, which is 5 volt. So now clearly if VD is greater than 5 volt, I am good. But what is the minimum VD in order to keep the transistor in saturation? So VD min is 5 volt, right? So what is the corresponding node? What is the corresponding node on the circuit on the right that corresponds to VD? Clearly this is VD. So that has to be equal to 5 volt. If this has to be equal to 5 volt, then what should VDD be? So VDD has to be 5 volt plus 25 milliamps times RL. RL is 1 kilo ohm, which means this has to be 30 volt. And so this is essentially VDD min, right? If you increase VDD beyond 30 volts, fine, your transistor will be in saturation more comfortably. But this is under the condition that the transistor is barely at the edge of saturation. Okay. So now the question is, what happens when I put the input back, right? What am I asking is, do you see an issue what I am essentially asking is this: do you see an issue if I put the Vi back in the network? So now what is VDD? VDD is equal to 30 volt. Right? VDD is equal to 30 volt. What is the drain voltage? The drain voltage is 5 volt. Right? So now do you see an issue if I put Vi back in the network? Let's assume Vi equal to Vi is a sinusoid. Vi is some sinusoid Vp sine omega naught t, where let's say Vp is equal to 100 millivolt. So let's say 0.1 volt. Small signal, I mean, I just applied a 100 millivolt signal. I mean, even though we haven't really established what is small signal, what value is small signal, let's assume for the time being that this is small signal. Again, I mean, please kindly bear with me. We will see whether this can be characterized as small signal or not after sometime later. Okay. So what do you think? Do you see an issue with this architecture if I now apply a sinusoid of amplitude 0.1 volt? I request you to think about it for a second, and we'll meet after that. Okay, so let's stop here. We'll see you in the next class.